Greetings, my name is Miha Luntinen, and if you're watching this, then you have probably come across our manuscript on a method for estimating charge breeder parameters with short plus 1 plus injection of metal ions. And you have found the GitHub repository containing the analysis code. And now you're wondering, could I use this code to analyze my transients? And the answer is a definite yes. And in this video, I'm going to show you just how to do that. So if you didn't find the manuscript or the GitHub repository, there will be links to them in the description below. But go ahead and download the latest release of the Consecutive Transients Analyzer. Download the source code from over here. I have already done that and put it on my desktop here. And you're also going to want to download a sample data if you don't have one of your own at hand. And make also an empty results folder in which to save your results. Then open up the code directory and find the GUI. Open this in terminal and execute the GUI, and this dialog should pop up. Now, first it's going to ask you to specify the working directory. Unless you are going to run the code somehow remotely, you don't need to touch this, but just so you know, it's the directory in which all the main routines of the code are saved. That is this one. But you do have to give the save to path, and I want to save the results on the desktop in the results folder, so copy and paste this path over here. Remember to add the / at the end so that the code knows that it's a directory. Click set, and that's set. Then select which routines you wish to run. For this demonstration, I'll select all of them, and proceeding from top to bottom, go through all these dialogues, inputting all the relevant information, starting with parsing. Now, you need to specify the path to the raw directory, raw data directory. That's the directory which contains all your measurement data. So the 1 plus beam, so the injected 1 plus beam signals and the extracted n plus current signals. So copy that, paste it here, remember the / and briefly about these data files, the code is going to expect that you have time in the left column and the actual transient signal in the right column. Now, all of these files follow a naming convention. I've got it saved in the measurement legend here. So the 1 plus files are named date dash placeholder pulse1plus.txt. Copy that and paste it over here. And n plus is named similarly just courant n plus.txt. Copy and paste it here. And in the placeholders, we input these file name variables corresponding to the measurement time. Copy and paste, hit accept, and the code will find the file names. The files have 0 length header, and as you saw previously, there's 12 lines worth of footer. The code will remove these, and the data file separator is, in our case, a tab, so /t. The conversion factor is the factor by which you have to multiply the transient signal in order to convert it to the units of amperes. This comes in our case from the fact that the current was measured against a 5.7 mega ohm resistor, which was in parallel with the oscilloscope's 1 mega ohm resistance. So that's how you calculate it. Ion species was potassium. Note that currently this version of the code only has cross-section data or rate coefficient data for potassium. Other species will be included later. If you have a specific need, let me know. Charge state data, we have data for 3 plus to 12 plus. So these are the n plus signals, 3 and 12. Hit save and proceed with the ABC fitting dialog. Since we gave the ion species and charge states just now, they don't need to be re-inputted. But we have to give the step size for the Runge-Kutta method. Just use 1 millisecond for this demonstration purposes, but you might want to use something smaller if you're really doing data analysis. In the manuscript, we used 10 microseconds. I'll save the ABC file as abc.csv. Yes, you have to put in .csv at the end. The file will always be CSV, but it needs that file type at the end, else it's not going to end well. Then the optimization dialog. ABC file is automatically inputted now that we are doing everything at once. You have to specify the electron density limits in the units of electrons per cubic centimeter. You can, if you wish, you can calculate the cutoff density corresponding to the microwave frequency that you've used automatically just by typing the frequency that you used in your measurements. Let's leave it at 14.5 gigahertz for now. The energy limits, we used the plasma potential order of magnitude in electron volts and up to 10,000 electron volts. Now you should be aware that the cross-section data only goes up to 10 keV. So this shouldn't be any bigger than 10 keV. Also, this corresponds to more or less the warm electron population, which is mostly in charge of the ionization processes. The solution set settings, finally, number of electron density array elements. I recommend to use 1000 here in any real scenarios, but because that takes quite a bit of time, let's use 400 for this case. Similarly, in Monte Carlo iterations, 1000 is good when you're really running the code, but it takes a long time to do all those, so let's just use 10 in this case. And you can select the rate coefficient evaluation method. Currently, I've got data for Maxwell Boltzmann EEDs. In the future, we'll add some others. Hit save and finally adjust the plotting settings to your liking. If you already had done the optimization once, you might want to just select. You might want to only do the data plotting. In which case, you could just designate the charge states for which you have got solution set files available, and then manually select the files to use. But now that we're doing all at once, the code automatically selects the charge states and the files. You can set limits on the results to consider in the plots. This doesn't affect the optimization, it only adds an additional constraint on the solution sets that you have already found. So if you want to see how the results are affected uh, if you just arbitrarily constrain the, for example, the electron density limits, you can do it here. You can set the upper limit of the penalty function. I'll leave it as 1 part in a million now. So this is the tolerance to which the penalty function has to be minimized. So if we use the 1e minus 6, it means that the penalty function is equal to 0 to 1 part in a million. The confidence, we use 34.1%, which means which corresponds to about 1 sigma in case of the Gaussian distribution. Of course, our results don't follow a Gaussian distribution, but that's the choice we make. The data point, we have chosen the median. I'll at some point add the ability to plot the most probable value, but for now, the median is the one that you can use. Finally, the things to plot: the solution sets, number of solutions versus the penalty function value, characteristic times, energy content, and the triple product. Let's just do these two now to save time for the demonstration. Hit save, and here you can set where do you want the parameters file to be saved. If your working directory is default, then just leave it as so. Click make YAML, and we should find that in here we have just updated our parameters.yaml file as we have. So now to actually run the code, open this location in the terminal and execute Python 3 master script.py, and as its argument it takes the params.yaml file. Hit enter, and the data parsing will begin. The code also tries to run some rudimentary tests to check that the inputs you have given make any sense. It usually works. At least it notices the most glaring errors. So we can already see that the data parsing is taking place. These are all parsed data files. Open that, for example, with the text editor to see that we have now time and current in a CSV file, as it should be. Here are some figures being plotted from the past data files, just to check that everything is running nice and smoothly. You can check that your signals are behaving as you expect. So t equals 0 corresponds to the 1 plus onset time, and the n plus transient begins after that, as it should, for each of the charge states. So that's done. It seems we have finished with potassium 12 plus, and ABC fitting has started. Charge state 4 plus has already been fitted. As you can see, the fit is pretty nice. There's some clipping happening at the peak, but that could also be due to noise. You might want to make sure of that by making the RK4 step size a little bit smaller to check. Here in 5 plus, there's something happening at the end again. This may be some kind of a boundary effect, but you might still want to check what happens with a smaller step size. 8 plus. I'll pause the recording until all these are done. Okay, so it seems to be all set now, and the ABC parameters have been found, and the solution sets are being optimized. Starting with 5 plus, we can take a look at the ABC file that we just found. And you can see here we have the ABC parameters for the charge states 4 plus up to 11 plus, and the corresponding uncertainties, which are generally small compared to the parameter values themselves. The chi-squared, the reduced chi-squared is close to unity, and in my experience, wherever it's bigger than 1, usually we are somehow underestimating the noise level in the data. By eyeballing, you can see that the fits are very good. You are given also the fit in a CSV file for each charge state if you want to plot those later on. The solution sets themselves are saved in these CSV files. While the 10 plus is coming up, we can check the fits. Even the 11 plus worked out quite nicely, despite the noisiness of 12 plus. As you can see, the fits are generally very pleasing. Indeed. Okay, so it looks like there was some trouble with charge state 8 plus. 8 plus is usually problematic because the ionization cross-section has an experimental uncertainty of about 200%. So 8 plus is usually the one that fails. If we had used a denser electron density grid and more Monte Carlo iterations, this wouldn't have happened. So that's why you have to use 1,000 by 1,000 iterations. But we can check the solution sets for all the other charge states: 5 plus, 6 plus, 7, 8, well, 8 was empty, 9, 10. And from those solution sets, we calculated the confinement times, charge exchange times, and the ionization times. And that's that. Hope you enjoyed. If there are any issues, feel free to contact me. Thank you, and